this assessment asks us to give the mechanism for the reaction shown on screen. Now, in the case that's actually done here, or that was done in the relevant figure in the book, it was intentionally giving one stereoisomer of the product. We're going to ignore stereochemistry for the purposes of this reaction. Now you'll see I've got it redrawn on the screen twice. I'm going to show this mechanism in two different ways. One using the non-ionic rendering of the Simmons-Smith reagent, one using the ionic. You'll see that our arrows are basically the same. And so we can draw this, when this carbenoid, the Simmons-Smith reagent, we can think of as both electrophilic and nucleophilic. We know that alkenes are relatively, I don't want to say good nucleophiles, but they're nucleophilic. We saw them attack tons of electrophilic reagents before. And so we can show this mechanism by showing the pi electrons attacking the carbon, kicking out the iodide, and these electrons in the carbon-zinc bond staying with carbon as they add back. That's going to give us the cyclopropane shown on screen. How could we show the same thing using the ionic form of the Simmons-Smith reagent? Well, now instead of having a carbon-zinc bond shown here, we're saying that there's a lone pair on carbon and a positive charge on zinc. This makes it even more obvious that having the carbon iodide is going to make this carbon an electrophile. Having a negative charge is going to make it a nucleophile, and we'll simply draw our mechanism this way, where the pi electrons attack carbon, push out the iodide, so these arrows are identical to the ones we saw in the earlier, and now instead of using the electrons in the bond, we're using this lone pair in this ionic molecule to add back. Either way, that gets us to the same product. Both of these mechanisms would be considered acceptable. If you're unsure which one your instructor wants, ask them.